So the last video was pretty, how do you say this? Was somewhat embarrassing, given we didn't score well on the quiz, so we have to revisit the whole thing again. But anyways, so I've given it a good time without like really studying about this. So let me close this now. And one thing that was clear to us is that the lack of information when it comes to domains and so basically, there is a way to solve for these problems in which you try to solve for, um, you know, you try to simplify the equation and then you eliminate the variable that exists by applying the inverse to both sides, and then you solve for x to get the domain. With that in mind, we can like quickly revisit the inverses again. So we know that algebraically is the best approach to get to solve for the inverse. And as you can see, you have the function of fx equals to x plus 3. You convert this to y, and then you solve for the equation. So you end up saying y minus 3 by solving the equation for x. So y minus 3 equals x. Now, you just have to make sure that you don't get a value. So given y is in the top, it can be 0 or negative, so any real number will suffice here. But if it was at the bottom instead of the 2, then it would have been a whole different story. And this is the list of inverses that you could use, with the important part being uh, illustrated here on this third column. So when it comes to if it's 1 over x, it becomes 1 over y basically. It's the inverse is basically the same. For f of x, y and y are non-zeros, x squared becomes the square root, x to the power of n becomes uh, the square, not the square root, but n root of the root of n for y, or y to the power of n. Like you have two different possibilities. Either case, none should be 0. Both shouldn't be 0. A to the power of x exponential would equal to the log ln. So there's the log. One shouldn't complicate the exponent with the log. The ln is the log of 10. That's why it's called ln. And this is the normal log. And it's like the square root and the nth root of y. A to the power of x, and then you have all the sines and cosines and tans reversed. Now, when we square root a negative number and then do the inverse, this happens. So when we have like negative 2 to the power of 2, you get the answer of 4. Now if you need to go back, you can't get to the negative 2, and that doesn't really work. So you have to make sure that for the negative numbers there is a way to reverse. So you need to either limit the domain here for numbers less than 0, and then always include a sign, the negative sign in front of the square root, or you should limit the input to only be positive numbers and leave this as is. Yeah, so he opted for limiting the domain to all x's greater than or equal to 0. That way he wouldn't have to worry about the negatives. And there is no, and something we should recall is that for bidirective functions, they can be inversible, but otherwise they can't, because there is a possibility of you landing two range values for the same input, which actually jeopardizes the results you're getting. It's like in this case, you got for the same range, you get two different values. So when you need to go back from the y to the x, you really don't know which one to go back to, either the x1 or the x2. And this could create problems for us. So this is the domain and that's the range, and that's how things actually work. Now, if you tend to plot these in graphs, which is this is a bit tricky. The last time we've done the quiz, the trickiest part was actually deciding where the y would be or where the x would be. But if you get the function right, you could like get a quick understanding of how the plot would look like, and then that's how would you actually do it. It's pretty, how do you say this, like in this case x squared would be like a half a parabola, and then the square root of x would be something like the square root of x is something like uh, this is the inverse of this. Now I'm not sure, if you may not be sure how this looks like, you could just opt in for the drawing here, and we've actually done this the last time. So this is the blue is the square root of x. It goes like this way, and then the x squared, and then the red line is the square root of x, which goes the other way. So you will end up scoring like you would have a mirrored shape, in which way if you draw a horizontal line, a slope that goes across these two, it's like mirrored shapes. And that's basically how things would actually work, if you ask me. Now keep in mind that this is for positive numbers. I mean, for negative numbers, the input would change, so the x-axis would actually change. The perception would change, so that's very important to limit the domain. Uh, so that's that, and then there are some irreversible functions like this. I didn't really try to solve this, but just keep in mind that some things are irreversible. That's that. So we could give the quizzes again another shot. Let's do that. Yeah. So here we are, the inverse functions. Back to the moment of truth. We need to have a paper and pen, so I need to get those ready. I didn't have them ready, so I'll get a pen and paper and solve for this again. So let's solve for this. So I've got the paper and pen. So let's solve for this. So we've got y equals 5x minus 4. So what's the inverse of this function? So I'm trying to adopt this algebraic methodology at all times, instead of me just trying to apply some tips here and there. Anyway, so this would be y plus 4 divided by 5, which equals x. So the inverse of this would be, so instead of f of x going from the domain to the range, we're going from the range to the domain. And for that sense, the range would be the value of y. So if we have the range, we can actually get the domain, the value of the domain. And in that sense, x equals y plus 4 out of 5. Nice. Quick results. I answered this before. Yeah, I know. I just want to redo these. I want to redo them again. Okay, that's question 1. Let's do question 2. What is the inverse of the function? I think we could like restart the quiz. Yeah. So I think it's the same quiz. Next question. What is the inverse of the function f of x? Let me check if we can actually use like an account and keep track of our progress. I'm not sure. Well, since we've started this, let's just finish this and then I'll explore this in my own time later. So f of x equals x squared plus 2. So y would equal x squared plus 2. Y would equal y minus 2 equals x squared. And then you just like take the square roots. Y minus 2 equals x. Now something we need to consider here is the domain. So in the question it says that x greater than or equal to 0. So it's all positives. And in that sense, the square root y minus 2, the values should always yield positive numbers. So y greater than or equal to. Now, so to get the 0, you need to have y being 2. 2 minus 2 is greater than or equal to 2, which is D. You're right. So let's quickly go through so till here we're fine. Things get complicated when we start to consider the domain. And so if you apply 2, must take note of the domain. Yeah, so x is greater than or equal to 0. Let's plot both in terms of x. So it's now fine. You can see starting off from 2 is greater than or equal to 2. That's what the graph is all about. Which is also half of a parabola. Note that the two curves are reflections of each other in the line y equals x. So when y equals x, that's when you get the separating line. Next question. What is the inverse of the function? So we've got y equals half 3x plus 4. Now, in order to solve for this, 2y, there's no domain here, so 2y equals 3x plus 4. We eliminated the half, and then it would be 2y minus 4 equals 3x, and then x would equal 2y, just switch sides, minus 4 divided by 3. So this would actually mean x equals 2/3 y minus 4. Y minus 4. No, y minus 2. Because it's 2y minus 4. So 2/3 y minus 2. It's all algebraically, done algebraically. So we've got like the 3x would equal 2y minus 4, and then divided by 3 to get the x on its own. You'll have x equal 2/3, and then you take the 2 being a common factor here. So it's 2 out of 3 multiplied by y minus 2, and that's basically it. Next question. Now this is where things get a little interesting when we get the domain included. So what's the inverse of the function? So we have y equals ln 5x minus 2. For the domain, x belongs to real numbers. However, x is greater than 0.4. Greater, so 0.4 is not included. Now, let's try to solve the equation first. Now, in order for us to get rid of the len, we should introduce the e. In that sense, e to the power of so the inverse of the len is actually e to the power of x. So e to the power of y in this case is not the x. E to the power of y equals 5x minus 2 because the e to the power of len actually eliminates both. E to the power of y equals 5x minus 2. E to the power of y plus 2 equals 5x. And then e to the power of y plus 2 divided by 5 would give us the x. And that's the inverse. Now, what we need to do, we know that the domain is x is greater than or equal to 0.4, right? Right. Now, in order for us to get the domain, so in the choices there is no domain over there. So does this mean that so we have x equals e to the power of y plus 2 out of 5. This actually means 1 over 5 e to the power of 2 plus 2, which is this one here, first a. And let's try to solve it now. It's correct. So we have y len of 5x, and then you inverse this by introducing the e to the power of x, which is e to the power of y in this case. Then e to the power of len eliminates both, so you'll end up having 5x minus 2. Now you add both sides, you take the 2 to the other side, and then you divide by 5. And that's how it is. It didn't consider the domain though here, so we got lucky. Next is that we've got y equals x cubed plus 5. Now x to the power of 3 plus 5, if you solve for y minus 5 equals x to the power of 3. And then, if you need to solve for this, you need to introduce so x to the power of n equals the root of n of x. Is that it? Yeah, I think that's it. So if we look at the inverses here, x to the power of n is actually the root of n to the y, or y over y to the power of n. Given the multiple choices we have is the roots of n to x. Okay, so when we apply this, we will end up having the root of 3 of y minus 5 equals x. Right, so now that's that. The root of 3 is not concerned, is not the square root, so it doesn't matter if the end result is negative or positive. So the domain should be all real numbers. So it's the root of I'm guessing it's this one. It doesn't really matter. Oh yeah. So we solve for it and we apply the x to the power of n will equal the root of n to y, the cube root. And I'm not sure that the plotting would actually, let's plot them in terms of x. So it's now, okay, so f1, f and f1 are the reflections. Now can we draw the cube root? Root a, b. So we could go like root a to b. A is like what? X minus 5. So x minus 5, and then we'll have 3. Let's try to plot this. And this is the red one here, x to the power of 3 plotted. So that's what we're getting here. So we should also introduce minus 5 or minus 10 and minus 10 because the cube allows negatives to have to exist. And this is how it looks like. So if we, yeah, it's basically the same. So the intersecting value here is basically the domain that we were talking about. Line y equals x. Note that in this case there are no restrictions of the domain or range. They are both all. Okay, did they limit the domain? Yeah, because it's cube. Next question. You see, I think if you get the trick, it would be like possible on how. So let's solve this one. It's like it's much more easier than the first time because not that I remember the answers or anything, but it's more like I'm more focused and it's like I'm following a path that I'm solving for, and it's much more clear. It's clearer now on how to actually solve these problems. Anyways, so without further ado, let's keep going. So the cube root here of x plus 2, in order for us to get rid of it, so we know that the inverse of cube root is x to the power of n. And in this case we have the y, so y to the power of 3 would equal x plus 2. And then y to the power of 3 minus 2 would give us the x. For all real numbers, it really doesn't matter because it's the cube. So it's this one here, y, that's the answer, inverse of x. Yeah, you get rid of this by getting the power of 3, and then if you try to plot these two numbers, the y to the x, this is when they form the inverses of each other. Reflections y equals x. I think the reason why they keep drawing this is the importance of having the graphs later on. But a way to plot the function, I mean, you could just simply, I mean, it wouldn't be easy doing it manually, like applying different numbers to both the equations from the domain, but it's easier just to use the tool and then have the graphs being drawn for you. And that's how you actually, like, I think they're using the same tool though. And I don't know, it just looked like it's using the same tool. I really like this tool. I really like it. I should bookmark it. Anyways, let's not divert of our main course, our main path. Next question. What is the inverse of the function So we get y equals x squared minus 3 for x is less than or equal to 0, right? So this is the domain for real numbers. So we've limited to negative numbers only. So let's go ahead and solve for this. Now y plus 3 equals x squared. Now we know we can't, let's solve for this. So the square root of y plus 3 equals x. And then there's something you should note here, which is the domain. We want to get negative numbers. And given it's a square root, it doesn't allow negative numbers. It's always positive numbers. Then we just add the and negative and only allow positive numbers. X greater than or equal to 0. Sorry, minus 3, greater or equal minus 3. And then add the negative right in front of the so it's negative, it's negative square root of x plus 3, but you start off from greater or equal negative 3. So we solve the equation like we normally do, and then you take the square root, and then the square root could be positive or negative. But given the domain is limited here by the negative numbers, and that's when you should specify the values as to be greater on. This is the intersection. They are inverses at x equals y or whatever. Yeah. Right. Yeah, this is interesting. Which of the following correctly shows the inverse of the function shown above? The inverse of the function shown above. They have to have an intersecting point of a slope. So this is not actually a slope. You can't really have a slope this way that divides both. It's not a slope. It's either vertical, and in this case it can only be our 2 points. So it's either this or this. The slope here is not really a slope, so this could be a slope. Reflections of each other in the line y equals x. So is therefore there, because the others are like reflections too, It's like reflections, but there is no slope. That's what I'm guessing. It should have a slope. Alright, so the other question, this is an absolute example. Example of using the absolutes. So we have y equals the absolute of x plus 4, right? And then we know that x should be greater than or equal negative 4. Now, if we try to solve for this, is there an inverse for the absolute? No, we weren't acquainted to it. So just assume that it's only that. So this means that it's only positive numbers. So I'm not really sure. Yeah. Even you're only applying x equals greater than or equal negative 4, then you will only end up having positive numbers. So y minus 4 equals x. And this is the inverse of the absolutes. But the domain, if you apply minus 4, the domain has to be plus 4. Plus 4. Greater than or equal plus 4. Then that's when you get the 0. Right? So it's y, x minus 4, for x is greater than or equal 4. Interesting. Now because this x is greater than or equal minus 3, assuming it's minus, now you should be able to get negatives here too, right? but you don't get negatives in the first place. You always get positives. This is interesting. So x is greater than or equal minus 4. If we take the minus 4 and apply it here, minus 4 plus 4, that's like 0. And then minus 3 plus 4, that's like 1. And on and on. It's not like you get any negative number anytime soon. So it's always positive numbers. And then, but what you need to know is that you want to get the negative 4 if you decided to get the negative 4. So y minus 4, the equation we solved for, x equals y minus 4. So if we take 0 minus 4, it's like minus 4. And to get the minus 3, yeah, so it has to be 0 greater than or equal to 0. So this is how we solve for the equation. That's what we get. Let's take note of the domain. Is greater than or equal to minus 4. So we should get the negative. We should get like minus 4, minus 3, minus 2, and minus 1 if we needed to. I'm not sure why this guy started off from. Oh, it's not. It didn't start from minus 5. It's just that the drawing is a bit confusing. It's actually starting from minus 4 in this case, and this is the minus 4, and it just goes on and on. It's an infinity. The inverse is at y equals x, right? I'm not sure how do you get. It's like, yeah, all right, it doesn't matter. Now, the final question. So y equals quarter of e to the power of x minus 3. So now let's solve for this. Let's get rid of the quarter. So 4y equals ex minus 3. So 4y plus 3 would equal e to the power of x. And now to get rid of the x, we do the inverse. So len 4y plus 3 equals x. Remember, len ex eliminates ln and ex, so we will be left with ln 4 y plus 3 equals x. And this is what we're solving for. And now what we need to do is we need to figure out the domain. Okay, so if y is 0, we need to get the line of 4. Let me get up and let me get a calculator. So before we get the calculator, let me just show you this like a quick reminder. Remember that ln of x equals x and e to the power of ln x. Eliminate both, so you'll end up with x. That's what we've done here. So we introduced the ln to the mix, and then we just got the x. So let's do line of 4 and see how much that equates to. So we know that the answer is ln 4y plus 3. So it's either, so this is not true. So it's going to be this, this, or this. Now we know the ln can't be negative, right? So it can't be negative ln like ln minus something. That can't happen. So this is a bit confusing. I'll probably get this wrong because I'm not sure how to solve this. Not to get the domain, I felt like I could just apply 0 to 4y plus 3 and get the ln of that. So if we apply 0, we will end up with 3, so ln of 3. So how much is ln of 3? Let me try to get ln of 3. So we get a calculator. This is the ln of 3, 1.09. That doesn't really help. It's not true. So is it domains with domain R? Yeah, why not? But what would you do for ln being negative? Did we write anything in the notes about ln being negative? Um, yeah, so okay. Let me like quickly Google if ln can be negative. The natural logarithm function is defined only for x. It's n-defined, so it has to be positive numbers. So this is not correct. So we're left with C or D. If greater than 0, so 4 plus 3, that's like 7. But what if you apply a value here that you want to go back to? So if we try to apply e to the power of x, like e to the power of x, e to the power of, say, 1, it's like 2.7. Now the domain here to start off with, this should take in any number, right? But the inverse, you can't really have negatives in len. So but minus 75 would get eliminated by positive. It's like y 0.75. Okay, so I've solved for this for y plus 3 equals ex. Then you apply the len to get rid of the ex. Then you could like len plus 3, that's the x. Now you plotted those graphs. However, logarithms are only defined for positive numbers. So 4x plus 3 is greater than 0. Oh, we've done this the last time, and yet we did it. Oh boy. So you kind of solved for the equation within ln that should be greater than or equal. Got it. So that's the inverse functions again. I think we've done a pretty good job with the inverse functions, and we could add this to the list of resources. I think we've got these. Yeah, we've got these here. We could revisit them anytime, like randomly visit them, and that's that. So great. So this is out of the way now. This is the inverse functions. It's out of the way. We've got increasing functions and decreasing functions. This should be like straightforward. Well, let's go through it and then end this video with this. So a function is increasing when the y value increases as x value increases. This is an increasing function. It's easy to see that it tends up to go up as it goes along, flat. What about the flat bit near the start? Yeah, there was a bit of flattening. Yes, it is okay when you say the function is increasing, but it's not okay if we say the function is strictly increasing. No fatness is allowed. Flatness. What if we can't plot the graph to see if it's increasing? In that case, we need a definition using algebra. So y equals f of x, that's something we know. When x is 1 is less than x is 2, then x of the function, yeah, will equal. Okay, has to be true for any x1 and x2, not just some nice ones we might choose. Let's try to find where a function is increasing or decreasing. So we have the function x cubed minus 4x. 4x is the interval between minus 2 and 2. Minus 1 is included in 2. So we want to know for this interval, starting from negative on the beginning of the interval. At x minus 1, the function is decreasing. Continues to decrease until about 1.2. Increases past x. So without exact analysis, we cannot pinpoint where the curve turns from decreasing to increasing. So let's just say within the interval, the curve constant functions is a horizontal line, which is not a this is a function. If it was vertical, it wouldn't be a function. The slope m tells us if the function is increasing or decreasing or constant. Okay. Strictly increasing and strictly decreasing functions have a special property called injective, or one-to-one, which simply means we never get the same y value twice. Can be reversed. We can go from y value back to an x value, which we can do when there is more than one possible x value. Alright, the graph of the function 3x is shown above. Okay, for what value of x is the function strictly decreasing? So strictly decreasing is from, I don't know, somewhere like -10. Strictly decreasing, right? We've got like two parts. Is this -4? Okay. Okay, so -4 and 2 inclusive. Is this the 4? So assuming this is like 2. This is 2, and this is 4. On the part of the curve shown in red, for values of x between -4 and 2, but not including 4 and 2, because yeah, that's where the curve is happening. The above shows part of the graph of the function. On what intervals is the function strictly increasing? Strictly increasing. So it's like from infinity to negative infinity to 0.5. And then we also have this part here, which is like 0.1, strictly increasing to 0.5. Yeah, it's a union, alright. No, you don't include those, and you definitely don't include 0. It's this one. The above shows part of the graph of the function. In what intervals is the function strictly decreasing? Strictly decreasing. Like, this is not it, this is increasing. So we've got this part here from 1.5 until, so it's like 1.5 until infinity. It says strictly decreasing. Union. We've got this part here, 3 and 5. Union 3 and infinity. No, no. Strictly decreasing, right? is the function strictly decreasing? So when it's decreasing from this value, like 0.5 to it's 1.5 to infinity. Okay, let's read it. Assuming 0 plus 0 here, 0 minus 0 plus 15, it's like 15, 1. So it's actually decreasing from infinity so it keeps decreasing regardless. So we apply negative 1, that's 1 minus 1, that's minus 3, plus 15, so 12. It's like minus 3 squared is like minus 9, minus 8, minus 6. I'm not sure if the negative here is on the square or like the result makes like a whole difference. Other case, so all the positives would lead to, like if you take 5 squared is 25, minus 10 is was decreasing, like it keeps decreasing. So I'm going to say from D. Can be factored to negative x plus 5. Yeah, and x minus 3. Therefore has its zeros at x equals 5 and x equals 3. And the maximum point when you take a negative number, say 4 or 2 for simplification. 2 squared is like 4, so that's minus 4. minus 4 is like minus 8 plus 15. Minus 8 plus 15. Should get an 8, right? Should get an 8, so that's like 2, 4, 6, 8, 10. 2. Wait a second. So minus 4, minus 4. So minus 8 plus 15. What does we do? If we go for like 6, it's probably the first time. Whoa. Strictly decreasing. X squared minus 3x minus 9. So we just take multiply this in here so that it will make things a bit simpler for us. Where's my pen? I've lost my pen. Let's see how it was solved. So it's all basically about plotting it. So if we plot it to make it a lot easier. Strictly increasing, strictly decreasing. Now, I'm not sure if this is really important to us, so I'm just gonna stop here because I don't see the value much where we could find this like super duper helpful. But again, it could be useful. Because it's like there's no way of solving this except like through the graph. You need to plot it, and then from the graph you'll get to realize that, oh, it's from here to here. Like we want to do it algebraically. We could like solve for this like half x to the power of 3 minus 3 out of 2 x squared minus 9 out of 2x, that would equal y, or f of x, and then you apply say different values of x. But how would you like know if it's strictly increasing or strictly decreasing? Anyways, we'll just like stop this here, and like just a quick glance at what we should be looking at next. So by injective, surjective, we've done all of these, so that's fine with us. That's the inverse here. That's the inverse, so we're good to go. Composition, we've done composition. I'm not sure what the hell is that. Ordering and equivalence relations. Alright, so just stop here for now, and we'll pick up on this on the next video then. Alright, cheers.